Hi, I'm Talia Nasi, and I'm a Senior Developer Advocate for AWS Serverless. Today, I'm going to be talking about events, queues, topics, and streams in your serverless application, all about how to pick the right serverless application pattern so different components of your serverless applications can communicate. My job is to build serverless things and then teach the world about them. Before becoming a dev advocate, I was a test engineer for a few years, and I worked at companies like Visa, Forbes, and WeWork. I also have my Twitter handle here in case you all wanted to contact me or follow me for more fun stuff. So, why are we here today? Building serverless applications is incredibly popular today and growing even more so, and there's a lot of aspects to it which are unique and maybe new for people. From an architectural perspective, how to build serverless applications and how to think about design is really important. And so I'm going to cover the different ways serverless functions are invoked and how different parts of your application can communicate via various messaging solutions. So when we say serverless, we mean it's the removal of server operations. And these are the four tenets that define serverless as an operational model. Firstly, there's no infrastructure to provision or manage. There's no servers to spin up, operate, or patch. There's no physical or virtual container orchestration. Serverless applications also automatically scale by unit of consumption rather than by server unit. And automatic scaling is a really big win because generally you create multiple MVPs and you don't want to build all of them out for scalability. Serverless also has a pay-for-value billing model, which means you only pay for what you use, not for idle time. So if you have an idea that's not taking off, some of them can get expensive. And what this means is that you can experiment more. So let's say I have an idea for a new feature and Eric has a competing idea for a new feature. So Eric and I can A/B test our features, and regardless of which feature has a higher conversion rate, it's not going to cost much because you only pay for what your customers are using. Lastly, serverless applications have built-in availability and fault tolerance, so there's no need to architect for availability because it's built into the service. This is important because, let's face it, unexpected things happen, things will break, data centers have outages sometimes, there's earthquakes, spaghetti and meatballs fall from the sky, so what do you do if the servers handling your project fall over? How do you know that all of your versions are all in sync with all of the regions? Have no fear, serverless is here, my friends. Serverless applications are composed of three things. First, we have the actual Lambda function, and a Lambda function contains your business logic and can be written in one of these 6 runtimes or your own custom runtime. It's made up of code you've written to react to something that happened, and that something that happened is called an event source, and Lambda functions are triggered by an event source. An event is something that happened. Maybe a file was uploaded to S3, maybe a DynamoDB table was updated, maybe something was added to an SQS queue, maybe a request hit an API endpoint. An event source is what triggers a Lambda function and makes it come to life. Then we have the destination, which answers the question, what do you want this Lambda function to do once it's invoked? Do you want it to talk to another service maybe? After the function is invoked, it's going to go and perform whatever it needs to do, update a database record, return something to a client, talk to another API or endpoint that exists somewhere, or maybe send out its output to another service. These services can be other AWS services or third parties that are integrated with AWS. When it comes to thinking about how Lambda works, as the focus of today's webinar, we're going to be primarily focused on some of the different event sources that exist, the things that you can use to trigger your Lambda function, what the differences are and how you can use them, and also choose between them. But also remember, Lambda can also send function results to other services, some of which are also possible event sources. So bear in mind during this talk how the various services work so you can also choose the best destination based on what your function needs to do next. So when you think of common Lambda use cases, there are several. First of all, the most common we see is a web or mobile backend, where a very common practice is to have a client on the front end, say a mobile or web app, and we use API Gateway as a serverless API service. Now, behind that API will be Lambda, which triggers when the API is called, and then maybe reads or writes from a database like DynamoDB. The second use case we see a lot is file processing. A file, say an image or a CSV file, gets uploaded to an S3 bucket. This then automatically triggers a Lambda function, which does some image manipulation, maybe converts it to black and white, maybe creates a thumbnail and places the new image somewhere else, or reads the CSV file and then parses it and stores some information in a database. We also see a lot of queue processing. As we get into the various patterns today, we're going to dig further into this, but the idea here is I can use SQS and queue up events and then trigger these and get Lambda to do some work on the events in the queue. Amazon Kinesis is for real-time stream processing. This allows you to ingest a lot of data at a time and is highly scalable. So you would use this for real-time ingestion of, say, click data for your website or sensor data from the tractors in a field or streaming lots of log data somewhere. Lambda can read the stream, analyze it, modify the data en route, and then do some analytics before sending it on elsewhere. Notification processing is a pub/sub service where with SNS, for example, producers publish something to SNS, and then other things like Lambda can subscribe to a topic and then be triggered when there's a new notification. EventBridge is a newer service, which we'll get into more detail later. But with EventBridge, you can receive events from AWS services, your application, as well as SaaS partners, and then route these elsewhere, including Lambda. We also see Lambda used a lot for scheduled tasks. Instead of having a server hanging around, something you need to patch and maintain, even if it's small and doesn't cost you much, it still needs care and attention, and it costs you a lot of money when it's not being used. So you can use CloudWatch to schedule Lambda functions with time-based events to fire at specific times and run your scheduled operations task. So as we start to think about how we build our applications, we're going to often need to use a number of different services which need to interact with each other. And so something we need to think about is the microservice. An example of a basic microservice is something like this, a serverless API-based microservice, which we talked about earlier. There's a client somewhere which needs to read from a database, so we build a microservice which has an API gateway. When a GET, for example, hits API gateway, a Lambda function triggers, which reads the data from DynamoDB and then returns the information to the client. Of course, as with all applications, this gets extended over time. You now need something to write data to DynamoDB. The initial thought may be to add more logic to our original Lambda function to handle the post to API gateway, but that starts to increase the scope of the original Lambda function, so we decide to split this out and add another Lambda function. So as you build out more functionality in your application, don't put it in the same Lambda function, but rather move it out to another. This is the basic idea of a microservice, where each Lambda function has its own job. This microservice pattern isn't just for Lambda, of course. In another example, you may need to separate out your DynamoDB table into separate tables for different functionality. One of the common questions we get is, should every service of mine talk to another using an API, and do I need an API for everything? Well, maybe not. In this talk, we're going to look at a number of other services, so you may not need to run your own API. There's a helpful conceptual way to think about how your microservices need to interact, especially with APIs. Think of an iceberg. Often what we see is customers have a collection of microservices that represent an overall product, or in bigger products, a component. There's a public interface portion of the iceberg, the bit that sticks out, which is your public-facing part, the API that customers interact directly with, so the endpoint where a web or mobile application would talk to, or another external component would interface with, the real customer-facing portion of an API. And then below the waterline, there's also the internal part of an application, which external users do not directly interact with. This is often the bulk of the applications. In fact, often very few services need a public-facing API. They may only need to pass messages to each other, not needing a fully fledged API. So if you're controlling all the various services that are being built as part of your application, and you have some level of organizational standards and communication, you often don't need to build an API between two private internal services at all. There may be other options for talking between services inside of a microservice architecture that aren't traditional APIs, and that's what we're going to talk about today. What services can you put between your different microservices to allow them to communicate, the ones below the waterline? And what are the features and benefits of the various solutions so that you can use the best ones for the job? We're going to talk about microservice patterns and how Lambda interacts with various services. Lambda has three execution models: synchronous, asynchronous, and stream. In a synchronous model, you have commands. You're telling a service to do something. Go place this order, go do this thing. It's command-driven. Lambda is made to execute and returns a response once the code has finished executing. In an asynchronous model, you have events. Events are something that happened that can trigger your Lambda function. Events within your application occur and are observed by services, but only triggers those services which are interested in a particular event. The response is returned upon invocation, and the processing continues in the background. Lastly, we have stream or poll-based architecture. Stream-based is where Lambda reads records from a data stream and invokes your function synchronously with an event that contains stream records. So these are the three main execution models: synchronous, asynchronous, and stream-based. And across these live a number of different services that can invoke Lambda functions. And today we're going to be focused on primarily the use of streams, SNS, which is simple notification service, SQS, our simple queue service, Amazon EventBridge, and then the Lambda API itself. So first, let's talk about the Lambda API. Lambda can run your functions in response to events from other AWS services, or you can use the Lambda API. The Lambda API is the way that all services interact with your code. All the invocations go via the API, regardless of which invocation model is used: synchronous, asynchronous, or stream-based. You can pass any event payload structure to the Lambda API depending on the needs of your application. For very large payloads, you can store these in S3 and pay a reference to the S3 object instead. Every SDK includes the Lambda client, making it easy to interact with the Lambda service from your code. Another option is Amazon SNS, or Simple Notification Service. SNS is one of the oldest services that we have here at AWS. It's used very heavily by customers of AWS, both large and small. And so SNS, the way we say on the marketing site for it, is a simple, flexible, fully managed publish, subscribe messaging and mobile push notification service for high throughput and highly reliable message delivery. Essentially, what that means is that you can publish messages into what's called an SNS topic, and then that SNS topic has the ability to then push or deliver those messages out to services that have subscribed to that topic. The publish is an asynchronous process, so once SNS has received the message, the publisher can carry on, confident that SNS will handle the message reliably. And so these can be HTTP or HTTPS endpoints, mobile devices, SQS queues, or in the case of what we're talking about here today, Lambda. So as messages are put into an SNS topic, the SNS service can then go and directly invoke a Lambda function with these messages, and then your Lambda function can consume that message, that record, or that data, and then execute upon it. And there's a few interesting things that SNS can do. One of them is that it has the ability to have multiple subscribers to a given topic. So let's assume that you have a really complex microservices environment. Let's say that you have a checkout process. You could put a message onto an SNS topic that says that an order was placed and it should be consumed by a credit card processing service, a shipping service, and an inventory service. So all of these are subscribed to this SNS topic, and they would all get the same message and then act upon it independently from each other, but again, still processing that single message. You can then do more sophisticated things on top of this as well, such as filter those messages so only certain subscribers get the message. Let's say that at some point somebody cancels an order and you only need to update some of those services. You can set to only filter based on a canceled order. Another service that's integrated very deeply into the AWS platform today is SQS, or Simple Queue Service. Again, the marketing site says it's a simple, flexible, fully managed messaging queuing service to send, store, and receive messages between software components at any volume without losing messages or requiring other services to be available. It's basically a managed queue service that allows you to publish messages to it. And the Lambda service can then pull a queue looking for new messages, and when it finds messages, will grab them and invoke the Lambda function on your behalf. Now, SQS is technically the first web service that Amazon ever launched, and it goes way back before actually technically there was an AWS as a business inside of Amazon. We actually just celebrated SQS's 15th birthday a few months ago. SQS is used very heavily internally at Amazon and at AWS and by customers of all shapes and sizes to do massive throughput of queued message delivery. Now, in regards to SQS and Lambda, it's pretty straightforward. You basically point Lambda at the queue, and what happens is the Lambda service maintains a puller that pulls the messages out for you. Now, those messages are processed in batches, and basically you're allowing the function to consume those batches, and then you can process the messages in the batch. SQS has two types of queues, standard and FIFO queues. Standard queues have at least once delivery. There's the potential for a message in an SQS queue to be consumed by more than one reader. As a large distributed system, it really favors durability and availability of the service, but what can happen potentially is there is a rare chance a message could be pulled out more than once, and so you do have to think about how that could impact things. SQS also now has FIFO queues, first in, first out, which do strictly guarantee the ordering of messages, as well as ensuring there aren't any duplicates. The trade-off is fewer transactions per second compared to standard queues. You can also use streams. Kinesis Streams is a fully managed, highly scalable service for collecting and processing real-time data streams for analytics and machine learning, and there's really all sorts of use cases here. The way it works with Kinesis is that as data is put into a stream, the Lambda service will pull that stream looking for changes, looking for new records that are being put in. It's going to pull those records out and inject them into a Lambda function via an invocation. Now, Kinesis is really good. It's a really good product that has a lot of different capabilities to it, and it's really meant for massive throughput, ingesting data, and potentially terabits per second. So with Kinesis, you create a stream, and then based on throughput, your stream is then split into shards, which have a fixed amount of capacity and throughput. Lambda will receive batches of messages off of those shards in parallel. So just like how SNS supports the ability of a fan-out model for sending messages to multiple receivers, what Kinesis allows you to do is have multiple consumers off of the same stream, such that you could have individual applications that are pulling in the same data. Now, in this case, there isn't really a way for you to filter those messages out to, say, prevent one application that's consuming a stream from getting some messages and not others, but this does support the ability for you to do multiple parallel application path workloads for things like near real-time analytics and data processing. So although we've talked about events in the generic sense of sending data to Lambda functions as an event which invokes a Lambda function, there's some newer options for processing events with AWS. In the standard microservice API world, you have directed commands. API thinking is synchronous thinking. You can't move on until the API response comes back. With APIs, you are sending commands. So go do this thing, go create this invoice, add this product to the shopping cart. It has an intent and it's directed to a target. An event is something that happened. Maybe a new file has been created. Maybe an exception has occurred or an error has occurred. Maybe a new customer has been created or a new order has been inputted into the system. It tells you a fact. Events are immutable, which means they cannot be changed. In practice, it's just a JSON object that tells you something that happened. And a lot of people get scared when they think of events and how to use them, but all it is it's an envelope with a description of what's inside, and then inside that envelope is a JSON object describing what the event is and what happened. So again, with events, you're telling a fact and others decide what to do with it. So let's think of an example of a coffee shop. So a customer comes in and orders an espresso. When the barista hears that, he starts making the espresso. And when the pastry guy hears that, he's like, you know what, this isn't a pastry, I don't care about this order, and he moves on. But if a customer comes in and orders a chocolate croissant, then the barista says, I don't care about that, it's not coffee. And the pastry guy says, all right, that's for me, I'm gonna start making the chocolate croissant. So they only care about things that affect them. With request-driven applications that use APIs, they typically use directed commands to coordinate downstream functions to complete an activity and are often tightly coupled. Event-driven applications create events that are observable by other services and systems, but the event producer is unaware of which consumers, if any, are listening, and typically these are loosely coupled. At Amazon, we have an event bus service that we use called Amazon EventBridge. Amazon EventBridge is a serverless event bus service that allows you to easily ingest and route events from a number of different places. These include AWS services and your own applications. It also has a number of native integrations with SaaS partners, and you can route events using rules directly to different downstream AWS target services, such as Lambda, SQS, Kinesis, Amazon ECS, AWS Batch, and many, many more. It was built out of the existing CloudWatch events, and it uses the same API. Just like SQS and SNS, EventBridge is serverless, which means it meets our 4 previously discussed tenets. There's no infrastructure to manage or provision, scaling is handled for you, and you only pay for what you use. EventBridge provides an endpoint where an event producer can send events. The event router manages directing and filtering those events to the appropriate downstream consumers, and consumers can get the events they care about reliably while the producers remain decoupled. Producers and consumers do not need to know about each other. Think about the barista and the pastry maker. This makes it really simple to add functionality to your application. You don't need to manage a complicated mesh of upstream and downstream resources. So again, think of our coffee shop example. The barista and the pastry maker don't need to know about each other. As long as they're both listening to the events, the orders are going to get fulfilled and your application is going to run successfully. Here are some more common EventBridge use cases. You can use EventBridge as an event source for Lambda to take action based on a specific event. So the event happens that fires a Lambda function, and then it does something with another service. You can also do things like workflows, which we just saw. Let's say an order is placed by a customer. You could use that order event to cause a payment workflow with step functions that might run their credit card info and so on. You can also integrate artificial intelligence and machine learning services like Amazon Comprehend and Amazon SageMaker. Let's say a customer opens a ticket with Zendesk and they are not happy. They use profanities and very strong negative wording, and so you want to catch the really aggressive customer service tickets and escalate them. Those events call Lambda, use Comprehend for sentiment analysis, and then take action on them. You can also use EventBridge to audit and analyze data or synchronize data from a third party like Datadog. So let's take a look at the architectural diagram for EventBridge. It's a simple, flexible, fully managed event bus router to connect applications together, and events are published to an event bus. And you set up rules which match against something in the event and route the event off to one of 17 services, one of which is Lambda, which can then process the event. And the handy thing with EventBridge is that you can have multiple event producers adding very different events to a single event bus and simply use rules to filter the events and then route them on. I also just want to call out something else with microservices. Although we've been talking about how to connect many microservices, there's also times where you may need more coordination than just set and forget asynchronous messaging between applications. And this is where AWS Step Functions shines. So Step Functions is a serverless workflow automation service, which is tightly integrated with Lambda. You create state machines which have tasks, choices, and branching logic to coordinate the components of a workflow transaction, and you can stitch together services such as Lambda. So how can we go about thinking about how to compare these various services? I just threw out a ton of services at you, and I know what you're thinking, like that's great, Talia, but how do you know when to use each one? So there's basically 6 primary criteria that I think about as a comparison. There's definitely other things that we could talk about, like maybe complexity, but these 6 are probably the biggest things to help people think about which services that you should consume. So we're talking about scale and concurrency controls, the durability of the data inside one of the services, the persistence of the data inside of the services. Then we're going to talk about the consumption model and how to think about applications that take data out of the services. Then we're going to talk about failures and retry handling. And then the last thing we'll talk about is pricing, which is definitely a factor that people need to think about. So I'm going to break down this chart, and we're gonna talk about the differences between all of the services in terms of scaling and concurrency controls. So when it comes to scaling and concurrency controls, first of all, to mention, all of these services are meant for massive concurrency. So there are AWS customers using each of these services in some way at really incredible scale. So you should feel confident that for almost any workload, you can make one of these services handle the concurrency and scale that's required for your business. Now, one aspect you may want to think of is that you may actually want to control that scale and concurrency. You may need to protect downstream resources. You may want to make sure you're not consuming data too quickly. And so the ability to control that scalability might be something that you should be thinking about. So with the Lambda API, the way that Lambda measures concurrency is with the actual number of invocations that are happening at any point in time. It's not a per second or a per minute time period. It's just the currency at any point in time. For each individual function, you have the ability to control the concurrency via something that is called per function concurrency throttle, which we're going to cover in a minute. And so for SNS as well as EventBridge, the service itself automatically scales. You never have to think about what's involved in scaling an SNS topic or an EventBridge event bus. When it comes to consumption of data out of SNS or EventBridge, the Lambda per function concurrency setting is really the only way you can configure how quickly you want to consume data. And with SQS, it's very similar. The service itself is just going to scale. Whatever you have to think about, you don't have to think about turning any knobs or levers in order to make SQS scale up and down. For the Lambda integration, you define the batch size, which is the number of records from the queue, as part of the single invocation payload. And again, you can configure per function concurrency setting to control downstream consumption. Kinesis is a little bit different. With Kinesis, you do have to think about the number of shards that you have in a stream, and so a single shard provides an ingest capacity of 1 megabyte per second, or about 1,000 records per second, and then an outbound of up to 2 megabytes per second of data. Basically, this means you can actually read from Kinesis slightly faster than you can write to now. And if you have multiple consumers off of a single stream and off the same shard, then they'll basically share that total output of 2 megabytes. And so that's why the output number is larger than the input number. So with the 5 different services, Kinesis is really the only one you need to think about when you think about the maximum capacity or throughput of the underlying service. With SNS, EventBridge, and SQS, it's going to automatically scale up to handle as much data as you can throw at it. Managing concurrency is an important aspect of running Lambda functions. Concurrency is the number of requests that your function is serving at any given time. And when your function is invoked, Lambda allocates an instance of it to process the event. When the function code finishes running, it can handle another request. But if the function is invoked again while a request is still being processed, another instance is allocated, which increases the function's concurrency. There's 2 types of concurrency controls available: reserved concurrency and provisioned concurrency. Reserved concurrency guarantees the maximum number of concurrent instances for the function. When a function has reserved concurrency, no other function can use that concurrency. Provisioned concurrency initializes a requested number of execution environments so that they are prepared to respond immediately to your function's invocations. To enable your function to scale without fluctuations in latency, use provisioned concurrency. By allocating provisioned concurrency before an increase in invocations, you can ensure that all requests are served by initialized instances with very low latency. If you don't know what capacity to set, or you need some assistance in setting capacity, another option is application AutoScaling. You can use this through the CLI or CloudFormation, but not directly in the Lambda console. You set a minimum capacity and maximum capacity together with a target utilization. The service will then respond to changes in demand and scale your provision concurrency appropriately. So for Lambda, you have reserved concurrency, provision concurrency, and auto-scaling. Next, we'll talk about durability. And when we talk about durability, we're talking about what happens once the request has been accepted by one of these services until it's been processed, essentially while it's in flight and while it's being managed by that service. So with the Lambda API, there's really no concept of durability because the service itself is highly available. It's built using the AWS best practices, but essentially when requests come into it, it's going to immediately try to process those requests. And so there isn't really this concept of storing those requests until they've been processed. In this case, a client will need to handle any sort of failures or retries that might occur. Now, for the rest of them, SNS, EventBridge, SQS, and Kinesis, they all provide durable storage of all the messages that they receive. Any message that's received is stored across multiple availability zones before acknowledging the receipt to the client. So the nice and easy short version here is that with these services, all the messages are replicated across at least 3 availability zones. And there is high durability. If you get back at 200 when you talk to APIs for these services, you can be confident that your data is securely stored until it's been processed. Persistence is a little different than durability. Persistence is the idea that the service will hold onto the data and potentially keep it available for a longer period of time. You might think that you always want requests to be handled as quickly as possible, and in many cases that's true. However, there's times when you have to think about failures, for example, and what has just happened to the request. Persistence in this case matters just as much as durability. If my downstream service has a problem, I want to make sure that it's going to continue to store data for me until I fix my problem. With the Lambda API, there's no formal persistence model. If it's accepted, it's going to handle the invocation for you. And we're going to talk about retries in a minute. There's no storage capacity inside the Lambda service for requests in flight. SNS and EventBridge are similar. There's no persistence model beyond the delivery retry logic. This isn't really something to use deliberately, though. SNS has a persistence time of 23 days for AWS managed endpoints like SQS and Lambda, and 6 hours for others such as SMTP, SMS, or mobile push. EventBridge will keep your events for 24 hours while it retries routing the event onto another resource. SQS, however, is a little bit different. SQS by default stores messages for 4 days, so you can write data into an SQS queue without pulling out any data for 4 days. Then you can begin pulling out that data as long as you can consume the data faster than it could expire in that time frame. You can also modify this and change the message retention period all the way up to 14 days or as low as 60 seconds. You can use this for various reasons. One of the things that we see customers often do is put data into a queue that may only need to process every now and then. Or if there's data that's only relevant for a specific amount of time and you're happy for messages to get expired when they're no longer useful. Another very common and effective pattern is to use SQS as a buffer in front of a service where they don't really know how heavy it might get. If you get maybe 10,000 requests per second for a small period of time, when you would normally get 10 requests per second, SQS would be able to take on that huge ingestion, and then you can just consume the messages at whatever rate your application can handle. Streams are similar. By default, the data is stored up to 24 hours, so you can also increase this to up to 168 hours, which works out to be 7 days via something called extended data retention. This does come out at an extra cost of 2 cents per shard, above the default 24 hours. This does give you a longer period of time to do this if you need to handle replaying data. So with SQS and Kinesis, data is stored durably in the queue for a longer period of time, which gives you options to consume that data in different ways. It's good to understand how persistence is different than durability in the sense that it isn't about the request that has been successfully saved by the service. It's more about how long it's going to stay available inside of the service, effectively a buffer before a potential message goes away. And so for consumption, when we talk about consumption, we're talking about how you would think about consuming records off of the service itself into a Lambda function. With the Lambda API, sync or async, a single invocation per payload that's being passed in, there's no option of multiple clients, fan out, or replays. And so for more complicated Lambda to Lambda workloads, Step Functions is your friend for orchestration. SNS is async and it fans out to multiple subscribers with the same message in parallel. You use message filtering on metadata to control which messages go to which subscribers. It's important to turn on message delivery status for tracking failures, which helps with debugging. EventBridge is also async. EventBridge sends events to Lambda. For SQS, Lambda maintains a poller that will poll your SQS queue and invoke Lambda on your behalf. Once Lambda has processed the messages from the queue, it can go back and delete the message from the queue. With SQS, there's only the ability for a single consumer to ever consume a message. Remember, with SQS standard queues, you do have the possibility of a message being delivered more than once, so you need to be able to handle that in your application. With Kinesis, Lambda also pulls messages from the shard and streams. With Kinesis, you don't actually have to tell the Kinesis client library that the messages are good. You just need to tell the Lambda service that the function has completed successfully, and it will use the Kinesis client library itself on your behalf to report back to the records that are being processed. Something to be aware of with Kinesis is that you do need to configure the batch size, and sometimes depending on how data was put into Kinesis, those batches may also contain other batches. So have a think about how much processing needs to happen within your Lambda functions. You also want to make sure that your applications can handle repeated event processes. With SNS, if a Lambda function is not available, or if Lambda is not available, SNS will try a whole bunch of different times with exponential backoff, up to just over 23 days before the message is discarded. And EventBridge works in a similar way, retrying to route events with exponential backoff for up to 24 hours for a specific invocation. One constraint with EventBridge is that if a target of an EventBridge rule is constrained for a long period of time, EventBridge may not retry delivery. For example, if the target is not provisioned to handle the incoming event traffic and the target service is throttling the request that EventBridge makes on your behalf, then EventBridge may not retry delivery. When a function is asynchronously invoked, Lambda queues the events before a separate process reads events from the queue and then sends them to your function. Lambda manages the function's asynchronous event queue and attempts to retry on errors. If the function returns an error, Lambda attempts to run it 2 more times, with a 1-minute wait between the first 2 attempts and 2 minutes between the second and third attempts. Function errors include errors returned by the function's code and errors returned by the function's runtime, such as timeouts. When using the Kinesis client library, it maintains a checkpoint of process records and will retry records from the same shard in order until the cursor shows completion. When a function is asynchronously invoked, Lambda queues the events before a separate process reads the events from the queue and sends them to your function. Lambda manages the function's asynchronous event queue and attempts to retry on errors. If the function returns an error, Lambda by default attempts to run it 2 more times with a 1-minute wait between the first 2 attempts, and again, like we talked about, 2 minutes between the second and third attempts. Function errors include errors returned by the function's code and by the function's runtime. This works well in situations where every invocation must run at least once. However, in situations with a large volume of errors, subsequent invocations are increasingly delayed as the backlog increases, as each new error places another retry event back into the event queue. You can now configure how long Lambda should retain an asynchronous event in the queue, up to 6 hours, and how many times to retry, up to the default of 2. There may be times when you don't want Lambda to retry a failed invocation. You may be able to handle that failure elsewhere. You can now set retry attempts to 0. A recently released feature of Lambda is Lambda Destinations. With Lambda Event Destinations, you can route asynchronous function results to a resource without writing additional code for your function. Lambda Destinations gives you the ability to handle the failure of function invocations as well as their successes. When a function invocation fails, after the Lambda function built-in retry mechanism which we just talked about, has completed or the event age limit was reached, Destinations routes the record to the destination resource for every failed invocation for further investigation or processing. An execution record is in JSON format and has the full event payload, which is very useful for further processing. For each execution status, such as success or failure, you can choose one of the 4 destinations to send the execution record, either another Lambda function, SNS, SQS, or Amazon EventBridge. Lambda can also be configured to route different execution results to different destinations. In this example, you can see a successful Lambda invocation gets sent to EventBridge, while a failed one gets sent to another Lambda function, which can then do something with the error. So previously, we always advised to configure a DL queue or dead letter queue for a Lambda function, and this would allow failed invocations to be caught. Destinations provide more useful capabilities than a dead letter queue and can be seen as an enhanced option. And so you really want to be prepared because things will go wrong in your applications, and destinations or DLQs can save your invocation event information, which gives you options to do some troubleshooting or retry whatever you were trying to do or fix whatever the problem is and keep your applications processing messages. With Lambda, SNS, EventBridge, and SQS, in terms of pricing, the first million requests you make are free per month. And for EventBridge and SNS, there's no charge for deliveries to Lambda. And with EventBridge, there's no charge for events published by any AWS service. Okay, so what do I do already? Let's talk about when to use EventBridge or SNS. EventBridge has more AWS sources built in and more SaaS sources. There are also more target integrations between a wider variety of services, including Step Functions. With SNS, it's fan out and it supports millions of subscribers per topic. But with EventBridge, you only get 5 targets per rule. SNS has many more subscribers, but with EventBridge, it's easy to distribute events across other accounts. EventBridge has rule-based content, not just metadata, and events are also JSON-based in structure. So what about these other services? CloudWatch Events was replaced with EventBridge, and you can only use AWS services as sources, and it only uses a default event bus, and there's no SaaS integrations. SNS is great for high throughput because it can have millions of subscribers to a topic with very low latency. However, you filter by attribute and there are limited targets. Kinesis is great for real-time processing at large scale, but you're limited to the consumers per stream. Kinesis is also not serverless. SQS is great when you need resiliency and ordering guarantees, but there's no filtering. So something to think about is what invocation resource is the right one for you? So some questions you should ask yourself is, how real-time is your real-time? And how synchronous is your synchronous workload? Can you pull for updates? Does order matter? What's going to break if your Lambda function has bad code? And then do you need to think about downstream services? Some more things to think about are all of the resources we talked about today. All of these services require little care and feeding in terms of management. You don't have to water them, feed them, and give them sunlight. They're fully managed by AWS. You just need a little bit of oversight. They're all HIPAA eligible and PCI compliant. They all support fine-grained permissions via the AWS IAM, Identity and Access Management, and they all have a pay-as-you-go model without commitments. So a summary of what we talked about today. There's many ways to get data between microservices. Kinesis, SNS, SQS, and EventBridge, and the Lambda API are just a few of the ways. You might need an API that you create for yourself, but we talked about a bunch of different options today. You want to think through and factor comparisons on scale, durability, persistence, consumption models, retries, and pricing. You're probably going to end up needing more than one of these services and potentially end up using each of these in some part of your infrastructure. Something we didn't get to talk about today is the SAM CLI, but if you have used SAM before, it's the serverless application model that makes it easier to build serverless applications. Also, serverless pricing models make testing new ideas low cost and easy to get started with. We have a ton of content and learning opportunities from me and my team. We have the entire serverless patterns collection on serverlessland.com, so be sure to visit us if you haven't already. Thank you all so much for joining me today. I'm Talia Nasi, and I hope you all have a wonderful day.